welcome to the video. Today we're going to be doing GPU programming because GPUs are cool. This is a notebook. We're going to be working with a notebook that's adapted by Sasha Rush, who is an incredible professor who created a notebook that does GPU programming with Numba, which is a Python binding for CUDA. And he's created a bunch of these really cool puzzles. So I recommend checking out his notebook first. Link is in the description. And yeah, today we're going to be doing it a bit more interactively with CUDA C++. We're going to be implementing both the kernel and the executor. It's going to be a bit more complicated, but hopefully this should give you good intuition on how to program GPUs at a lower level. And yeah, let's get started. Oh, by the way, full flow for the win. Great engine type. Yeah. All right, let's get started. All right. To get started, I'm going to be going through this notebook that I created. First, we're going to change the runtime. So we're going to go here. We're going to change our runtime type. We're going to change it to a T4 GPU, and we are going to save. So with the T4 GPU, you're going to get a lot of warnings that I mentioned in my notebook of an issue where Colab says you're not using the GPU, but this only works with the GPU on. So it may not be registering as the GPU running. However, you still hit the quotas, which is a big issue, even though it says you're not really using it. So, all right, yeah, let's get started. So first, we're going to be seeing if NVCC is installed. NVCC is the NVIDIA CUDA compiler. And yeah, you see it's installed in your system. If this is not installed in your system, this will not work. So please get it checked out and get it to work. All right, cool. So we're going to be implementing the first puzzle. Puzzle one, which is a map, is we're going to be implementing a kernel, which is a type of GPU function that adds 10 to each position of vector A and stores it in vector C. And we have one thread per position in this case. So yeah, we're going to be writing this in C++. Well, technically it's CUDA C++. So there are small differences that I will be walking you through in this video. For example, indexing. 2D indexing does not work with CUDA C++. It may in some weird cases, but essentially we have to convert the index to something that's a single number, which we do later in this video. So first, we're going to add, we're going to create this kernel, right? Now, this is really simple. The first thing we want to do is we want to initialize the threads. So we're going to do this syntax, which is integer I equals thread ID x dot x. So this is initializing a single thread and assigning it to number I, so that then we can use I as our threads across the entire computation that we will program as well. So all we're doing is adding 10. So we're going to make this simple. And we're going to add 10. Now you're thinking, hey, you know, in normal programming, in order to make this work, I would initialize a loop that goes from I to the end of array A and then adds 10 to it and assigns it in memory to C. But the way GPU programming works is essentially I is your range. And so we can assume one thread is working on one index. So one thread is working on index 0, index 1, index 2, index 3, and outputting it to the corresponding location in C. And so we will show this when we create our, using our main function. So first, we're going to introduce a constant n equals 3. And then we're going to initialize an array A. And this is just an initialization, so this is not really super necessary. For you to know, this is not like super important. We're going to static cast this to a float of I. Cool. All right. Now, we're going to initialize the device arrays. So in GPU programming, and we're going to see this a lot, there's a host device and a device, technically. It's funny naming. The host device is your CPU, and your CPU is going to send over your instruction or kind of some schema to the device, which is your GPU. It's going to send over things that you initialized in your host. So I'm going to initialize arrays. It's going to send that over to the GPU. GPU does the computation, does the work, and then sends it back to the host. And then the host outputs it sends it to other places. In this case, we're just going to output it. And yeah, so we're going to initialize two pointers, DA and DC. In CUDA C++, pointers, instead of going like this, they actually go like this, which is quite interesting. That's something about device arrays, or about devices. So now we're going to use something called CUDA malloc. CUDA malloc is what is going to allow us to initialize it's going to initialize the how much memory we're going to allocate to DA on the device. So we're going to do that again with DC. Now, even though we didn't initialize DC, we're still going to hold memory for it because we're going to do stuff with it on the device. So I initialize it to n times the size of float because there are n positions that we're going to output A in. We're then going to copy this onto the device. So this is the most important part, which is how something on the host goes to the device. So we're going to do a let me do that, and then CUDA mem copy host to device. All right, so this is important. So we have DA, which is our device. We have A, which is what we're going to call it on the device. So do you see here? A, A, A. That's what we're going to call it on the device. It's going to be n times size of the float, which is how large we want it to be. And then CUDA mem copy host, which is your CPU, to your device, which is your GPU. And then we're going to do the actual function. This is how you instantiate a kernel. We'll talk about what's in these brackets later. It's just the number of threads and the number of it's the number of threads per block and the number of blocks per grid. We'll talk about those concepts a bit later, but we don't need to know that at the moment. So we're going to pass in the ADC. Then we're going to do a CUDA mem copy. So it's DC has been manipulated on the device, and now we're going to copy that to back. We're going to copy that back to the host. So we're going to do C, DC, n times size of float, and CUDA mem copy device to host. Very cool. Then we're going to free these from the device. From the host, actually, because we don't need these anymore. We've copied it. And now we're going to test this. So this should work. This will take your array. It'll send it to the kernel, put it in C, and get it out of here. So I is less than n, I plus plus. We're going to assert, which is why we imported C assert at the top. We're going to assert as C equals AI plus 10. So we're going through the loop. This is a kind of hard-coded version to make sure that this works. Map is successful. This is just for my own edification to make sure this is successful. This is not really necessary to the actual kernel. And then we're going to return 0 because it's not a void function. This is an int function. Okay, cool. You see what we did here? We initialized an array A. We created stuff on the host. We malloced that to the host with n times the size of the float. We then mem copied that to the device, from the host to the device, did the operation, copied it back from the device to the host, freed it on the host, checked an assertion, printed it out, returned 0. So this should write to a file called map.cu, and then we're going to execute this. And what we're going to get is we're going to get C is undefined, which is not great. That's not what we want. Got to initialize C over here. Let's do that again. We're going to overwrite that. And this is successful. So great. We implemented a map kernel, which is super neat. Map is successful. This over here is an important line. This compute sanitizer is going to help us throughout this video, and it's going to help you determine any memory issues that you might have in your program. If you're writing to memory locations that don't have anything or just don't exist, you're going to get these errors here. This is developed by NVIDIA. This is really cool. All right. Next, we're going to be implementing zip. So zip is different. Zip is you're going to add together the position of A and B and stored in C. You have one thread per position. Okay. The kernel is going to be super simple again. Integer I equals thread ID x dot x, and then ci equals ai plus b bi. And essentially, all of this is going to be the same. So we're going to literally just copy all of this, right? Right? But now we're going to initialize bn. Oops. Yeah, we're going to initialize bn. We're going to say also bi equals static cast floats, right? Cool. And then we're going to do db. We are going to CUDA malloc this, right? And then we're going to mem copy this to device. And then, yeah. Okay, and then we're gonna pass in db in here. We're gonna copy C out. We're gonna CUDA free db, and then we're gonna assert that AI plus BI, bam, 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 bam. All right, so does this make sense? All we're doing is just adding another memory location for B. Instead of 10, it's going to be whatever's in B. We're going to initialize B the same way we initialize A. And this should be an extremely simple way to do this. We're going to write to zip.zpu or .zip.cu. .cu is a CUDA C extension, by the way. We're going to run this, and there should be no errors. Okay, sorry. This should be zip. That's what you get when you copy and paste. We're going to overwrite, and this should be successful as well. And yes, we've got success. All right. Now we're going to do guards. Guards is an extremely interesting concept. So implement a kernel that adds 10 to each position of A and stores it in C. You have more threads than positions. Cool. All right. Let's imagine you have a pillbox. Pillbox has 7 positions in it. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Now, let's say the doctor gives you a pill and says you have to take this for 9 days. But you only have enough room in your pillbox to put one of those types of pills in there. So you're going to have to put each pill in the pillbox, right? But then after you finish the first 2 days, you're going to put the second 2 pills in there to reset the cycle and to make sure that 9 days can fit in your pillbox and you track your medications properly. Yeah, that's probably a really shit example. But anyways, excuse my language. But anyways, we are going to initialize a thread ID x.x. So essentially, we just want to check, right, if I is less than size. Now, what is size? Size is going to be your array. So we're only going to use threads. Let's say you have the pillbox of 7. You're only going to use threads up until 7. Equals AI plus. This just like checks memory bounds, right? We're gonna do something cool with the compute sanitizer in a bit. Okay, so we're gonna copy the first one because it's just the same example, except one thing is we are going to make this instead of n, which is the number of size, we're going to make this egregious, like 10, right? And yeah, this should be guards is successful. By the way, that I said this should be zip is successful. But anyways, yeah. So when we do this and we execute as well, by the way, this should be guards. Let me overwrite that. Thank you for catching that. Yes, okay. We're gonna do and cool. We're gonna get success, which is awesome. Literally the same thing. Malloc, yeah. But what happens if we remove this? So let's check the compute sanitizer. Right? We're gonna overwrite this. Watch what happens with your compute sanitizer. You're gonna get a huge amount of issues. Take a look at this, right? Invalid global read, right? And 0x40, invalid global read at 0x40, invalid global read by thread 5, by thread 4, by thread 3. What does that mean? We have a constant of n equals 3, which means that threads 0, 1, and 2 are going to be reading, but 3, 4, 5, 6, 7, 8, 9, and 10, or sorry, not 10, just 9, are going to be screwed. So we're going to change this back. We're going to add the condition around size. Yep. So let's run this again. We should be good here. Wonderful stuff. Now we're going to move on to map 2D. So 2D is quite interesting. So we're going to implement a kernel that adds 10 to each position of A and stores it in C. Input A is 2D and square. Square is going to help us a lot here. You have more threads and positions in this case. So 1D indexing doesn't work for 2D arrays in CUDA C++. From I and j, you can compute the index as I times size plus j. So we're going to add to int, we're going to int local I equals, thread ID x dot x and int local j equals thread ID x dot y, dot y. And integer index equals local I times size plus local j. Quite cool. Now we're going to add the same guards that we did above. So if local I is less than size and local j is less than size, right? We want to make sure that C index equals A index plus 10, right? This is your kernel. Quite simple, right? Essentially, I is thread idx.x, j is thread idx.y. Will take you along both dimensions of your size. So think of that as the x and y dimensions of your map, or of your 2D array. Then we're going to calculate the index and then add the index to that. So this is interesting. So we're going to do const int size equals 4. We can't copy what we did before. So we're going to initialize 2D arrays. Then we're going to say for integer I equals 0, I is less than size, I plus plus, for so we're just initializing it randomly. There's no real reason why I'm doing this. I'm just doing I plus j. Yeah? Cool. Now we're going to do float dA dc. Then we're going to do CUDA malloc dA size times size of float. That's the number of positions. You always have to have a memory number for the amount, or memory amount for the number of positions. Yeah, so we're going to do size times size here times size of float. All right, we're going to do something here. This is quite new syntax. We're going to create a dim3 type, which is a dimension that can be passed into when we instantiate the kernel. So when we do map2D, so I'm going to do dim3 equals block dim size. So this will situate, or will give you the number of threads in that block size across those block indices, or the array indices. So this block dim is extremely important. It will not work otherwise. So we're gonna mem copy this size times size of floats. CUDA mem copy host to device. Bam. Okay, now we're gonna do map to D, one, block dim. Super important. Why we have this? Because we have one thread per position here, right? Then we're gonna do CUDA mem copy. C DC size times size of float, and CUDA mem copy device to host. Wonderful. All right, CUDA free DA, CUDA free DC for integer I. We're gonna just read those. We're gonna again check the assert statements. Assert CI. See, we can do this on the host, but we can't do this on the device. That is super important. So the reason I can do this, which is the double indexing over here, is because we are on the device, which is the CPU, by the way, not on the host. Or sorry, we're on the host. Do you see this warning down here? Yeah, Colab is something else, I tell you. We can do this on the host, which is the indexing, but we cannot do it on the device. So we're going to do SCCL 2D mapping is successful. Right, and then we're going to return 0. I don't know why I'm doing return 0, but it's okay. So we're going to write this. This should work. 2D mapping is successful. Bam. So do you see what we did here? Very simple. But this is introducing the 2D, how we can map 2D, work with matrices instead of just arrays or vectors. We have the thread indexing over both dimensions, X and Y. We check the guards over here. We also have a float here. We malloc the size amount that we want. We mem copy the size that we want. We mem copy it back. This block dim will allow us to initialize the number of threads along the number of dimensions in a 2D format, which is great. And then we check and we make sure it's good. Yeah. So let's do broadcasting. So implement a kernel that adds A and B and stores it in C. Inputs A and B are vectors. You have more threads than positions. Again, super easy. However, this indexing gets quite a bit weird. So imagine you have A and B, stores it in C. We're going to add it in an interesting way. Let's get going. So we're going to do integer I equal, let's call this local I equals thread ID x.x, integer local j equals thread ID x.y, integer index equals local I times size plus local j, right? Now, if local I is less than size, sorry, used to Python, local j is less than size, C index equals, why am I doing this? And I will explain in a sec. Local j. I and j are working on, even though A and B are on the same size, or are the same size, I and j are working on threads that are the same size. So, and since A and B are both vectors and not a 2D matrix, we do not use the normal index. We just use local I and local j to index through A and B, and then add it to the appropriate index in C. So it should be good, right? Now we're going to initialize this, have a good time. So constant integer size equals 4, float A size 1, right? B, this is how you initialize. So these are vectors with 2 dimensions. MATLAB would have a field day about this. For integer I equals 0, I is less than size, I plus plus. We're going to do A, I, 0, oops, equals static cast float. All right, I could put this in the same loop, but just for kick's sake, for demonstration's sake, I'm gonna add it out here. Cool. So B 0 J, oops, equals static cast float J. Okay, very cool. Now we're gonna make float. Right, and then we're gonna do CUDA malloc. All right. Oh no, that's not what I want. Right here. Okay, cool. All right. This should be C, C, and this should be size times size. This is good. All right. We're gonna do this again. We're gonna copy. Bam, bam, bam. All right. Again. Nice. Now we're gonna do dim3 equals block dim again. You know why? Because we have C, which is blocked in size 3 by 3, or n by n, technically, whatever. We're gonna do broadcast 1 block dim, and we're gonna do DA, D, B, D, C, size. CUDA mem copy T, size, ooh, size times size times size of. Well, I know the parentheses are not doing anything, but this is just from readability. Yeah. All right. Bam, bam, bam. All right. CUDA free, and CUDA free. Yeah. So this is your main. You're gonna add the assertion statements. I'm a bit lazy, so we're gonna copy it from up here. And we're gonna do bi0 plus b0 j. All right, and we're gonna add it here, and we're gonna say broadcast is successful. Oh, CUDA malloc has too many. Ah, yeah, that should not be there. Sorry, I have to. Should not be equal. There we go. This should be fine. Good. Broadcasting successful. Does that make sense? We are indexing across two different dimensions of A and B, and then broadcasting them to make C, which is a 2D matrix. Puzzle 6 is blocks. So, blocks is easy. Implement a kernel that adds 10 to each position A, stores it in C. You have fewer threads per block than the size of A. Remember, a block is a group of threads. Threads per block is limited. You can have many different blocks. So essentially, you can have many different, yeah, you get it. You can have many different blocks. So like let's say you need to do something on an array of 8, but you can only have 3 threads per block, then you would need 3 blocks. That math is super important. We're gonna be adding that math to determine how many blocks we actually need. You can use only some of the threads in a block, but you can't have more threads in a block than what you're issued. And you can't assume that you can do computations on more threads per block than you're actually issued. So this is a new way. So before we did this, right, we're going to add something to it to make sure we have correct block identifiers or block indices. So this is the way to get an integer I across your blocks and actually calculate the block. So like block 1, block 2, block 3, and then thread 1, 2, 3, 1, 2, 3, 1, 2, 3, or 0, 1, 2, 0, 1, 2, 0, 1, 2. Yeah, so CI equals AI plus 10. Yep. That makes sense? Same stuff. All right, now we're going to do the same thing as we did up here earlier. So this is for mapping. It is the same thing. So we're going to copy that in here. What is the difference now? We actually care about this. So these for right now are unknown. How do we do this math, right? So let's say we can make this up. So let's say threads per block equals size minus 1, which means size is 3, 2 threads per block. We're going to need multiple blocks. Now, how many blocks do we need? Well, we have 3 threads that we actually need. Each thread, there's 2 threads per block. Therefore, we can't just use 1 block. We don't need 3. We're going to have 2, right? Which gets 4 threads, and then that way we can we can create we can have as many threads as we need to actually do operations across an array size of 3. So how does that math work? Blocks per grid equals what? We're going to do size plus threads per block minus 1 divided by threads per block. Now, what is that? All right, so let's say size is 3, threads per block is 2. 3 plus 2 minus 1 is 4. 4 divided by the threads per block is 2 is 2. There we go. We also make sure blocks per grid is a whole number by doing it this way. Size plus thread per block minus 1 will always be divisible by 2. Or, I mean, in this case, will always be divisible by 2. But in all the cases, will always be divisible by threads per block, which is what we want. We want a whole number, which is essentially rounded up. There are other ways to do this, but this is the fastest way to do it. So, or at least the way that I did it. So blocks per grid goes in the first one, and threads per block goes in the second one. Yeah? So we have all this, blah, blah, blah. We're going to say blocks is successful, and we're going to run this, and we should get, we have some issues in here. Oh, that should be an if. And there should be some more errors. Identifier size is undefined. That should be size. Let's just call this size. Let's actually not change all of size. Let's call this n. Yeah. Let's call this n as well. All right, cool. That should work. Minus this. And blocks has size. So we're going to add n to the end of this. Good. Blocks is successful. Does this make sense? Right? So, all right, cool. Let's do 2D block, right? It seems like I've forgotten the function initializers. So this is going to take float A, float C. Ooh, sorry. Same thing in 2D. So integer I equals, let's call this local I, my bad, equals block dim.x. This is what we did last time. We're going to do the same thing. All right. All right. Does that make sense? Yes. Okay, cool. Size and local change the size. We are going to C index equals A index plus 10. Super simple kernel, right? Very, very simple kernel. Now with this kernel, we are or with this initialization, we are going to take the 2D initialization from before. No, not this. This one. Yep. Okay. Let's make this 6. It's a bit bigger. Now, we're going to do this quite interesting thing. We remember dim3 from before? We're going to do the same thing, except threads per block is size minus 1, size minus 1. And we're going to do the same calculation, right? Dim3 blocks per grid. I'm just doing this because I do not want to add another variable. I am lazy. Size plus threads per block. Y minus 1. Threads per block dot y. Got it? Very cool. Now we're going to do the same thing. We're going to do CUDA. Everything here should be the same. So let's just do except this is going to be threads per block and blocks per grid. Put it free. This is going to be map 2D block. And this should have, yeah, map 2D. 2D mapping is successful. There's probably some errors here that I oversaw. But anyways, no. Anyways, okay, cool. We are set. Does this make sense? All we did is the same thing, except we're going to initialize the 2D dimension that we've talked about before with threads per block, which is going to be 2 by 2 because I'm just, this is arbitrary, by the way. I just want to make sure. Arbitrary. If you have a threads per block greater than the amount of places that you have, then you don't really need blocks per grid. You can just say 1 block, which is what we did earlier. But this is completely arbitrary. Threads per block, size minus 1, size minus 1, and then blocks per grid on top of that. So, yeah. Wonderful. Now we're going to talk about shared memory. This is one of my favorite topics. Implement a kernel that adds 10 to each position of A and stores it in C. You have fewer threads per block than size A. This is totally normal. We've done this before. We don't need shared memory, but we're going to use it anyway to help us do this. All right? Sounds good? Yeah. So this is how you initialize shared memory in the kernel. You're going to do extern shared float shared mem. Right? Now you can use the shared however you want. Right? we're going to initialize two variables, I and local I. This will help us distinguish between threads that are between I, which is working globally, and local I, which is working locally. One thing is that when we talk about global reads versus shared reads, we usually want to minimize the amount of shared reads that we have. Sorry, we want to minimize the amount of global reads that we have. Shared reads can be whatever, but global reads there should not be that many. That's just convention. I think there may be some other reason, but I'm not sure. We're gonna essentially copy the contents of global or memory or A. We're gonna copy it to shared mem, and we're gonna do this. This is the most important thing. We're gonna wait for all of that to happen before we actually do any operations on the thread. So we want to make sure that thread 0 finishes that task and stops and wait for the other threads until moving on to the next operation, because you get jumbled up with indexes and everything, and it's not good. So we're going to add this command here. Sync threads. Super important command. This should happen so that all your threads stop at the same time. And then continue after that. I is list. We're going to do ci equals shared mem local I plus 10. Cool. This is your kernel. We're going to go back to main, and it's going to be the same thing. It's going to be the same thing, right? As this. Okay, let's call this 4. Set the same thing. We're going to add a line after here. I'll explain what that is in a sec. Let me do this as shared. We're going to add something after here. We're going to add that later. And then we're going to do, what is this? Shared. Shared is successful. All right. So, we need to initialize how large shared memory is. What size should it be in our kernel? So we're going to initialize something. We want the shared memory size to be the size of threads per block. We need to have the shared memory to be the same size as the number of threads. And it can be overwritten, it can do whatever, but we need it to be the same size as threads, because that's what we have access to. So to make it larger, we can make it smaller, but we're going to do it the same size as threads per block times the size of float, obviously. Then we're going to add the shared size. We're going to assert this, so this should be correct, and shared should be saved. Yes. Okay. This shared size is super important. We're going to always set it to threads per block times size of floats, and then it's overwritten and used as much as possible. We're going to see that later on, but over here, we want it to be the same size as threads per block. Yeah, wonderful. Now we're going to move on to pooling. Pooling is really cool. MO is a kernel that sums together the last 3 positions of A and stores it in C. You have 1 thread per position. We're not going to worry about blocks per grid. We're not going to worry about threads per block. We're going to assume it's the same size. The one thing that we are going to worry about is shared memory, and then also the logic of how we're going to actually make it such that we're going to add the last 3 positions of A and store it in C. Yeah, we're going to initialize shared memory as we've done before. Right? Then we're going to do integer I equals block dim x times block id x dot x plus thread id x dot x. Oops, sorry. Into the local I. Right? If I is less than size, we're going to copy that over to shared memory. We're going to sync threads after that. Then we're going to do if local I minus 2 is greater than equal to 0 and I is less than size. What are we going to do? That's just saying local I. Local I minus 2 is your last three indices of A. Local I minus 2 plus shared mem local I minus 1 plus shared mem local I. This is probably one of the most jank ways to do it, but it is okay. We will roll with it. Now, this is going to be the same thing as adding stuff. So we're literally just going to copy this from up above because it is the same thing. N equals 4, blah, 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 static cast, blah, 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 copy the M, threads per block, shared. We're going to say this is the same thing. But let's just say this is N for now, right? Let's just say this is N for now. It's fine. We're going to end, this is going to, because this is N, this is going to end up being 1 anyways, so not an issue. Think about it. If N is 5, 5 plus 5 is 10, minus 1, 9, 9 divided by 5. Since integer division, it's going to round down, it's going to be 1. It should be pooling. Yeah. This assertion is going to be different. So it's going to be if I. It should work. There we go. Pooling works. Does that make sense? This logic should make sense. Quite simple. All right. Now let's move on to the dot product. Yes. Everyone's favorite computation, dot product. Now, this is a little bit simple. However, we want to make sure that our kernels initialized properly, yeah? So we're going to do shared memory again. Integer I equals block dim x times block id x dot x plus thread id. Local. Again, we are copying to shared memory. We're going to say if local I is 0, integer sum equals 0. My bad. Let's go back here. We need to do the multiplication operation here. And then we're going to go through and calculate the sum. I'm going to say, after the for loop, C 0 equals sum, because C is not initialized to be that much. Yep, so let's do this. Let's use another one. Let's use this, actually, because it was quite good. We're gonna make C1 because we're only storing one number, which is your dot product, right? Let's call this 8 actually. Size. Let's just do I equals I, BJ equals J. So DA, DB, DC, blah, 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 blah. And then we're going to copy this from up here. Over here. Except we're going to replace N with size. Ooh, what's going on? Okay, cool. And then this is in here. It's going to be blocks per grid, threads per block, and shared size. Yeah. This is going to be dot product. Again, if you want intuition into this and more of the memory and things like that, please do Sasha or Dr. Rush's or Sasha Rush's notebook. It has these really, really neat visualizations that show you blocks and what's being written, and it shows you arrows, and it's truly amazing. So I would go ahead and check that out. Because I know over here it might be hard to see with the C++, but with the visualizer that Dr. Rush has, it's really easy to gain a grasp of this, especially when we move on to 1D convolutions, prefix sums, things like that. So yeah, okay, cool. We're gonna do this should be dot products. This should be dot products, and this should be integer expected dot. All right, we're gonna do this expected dot product plus equals a k plus b k. Yeah, and we're gonna assert C0 equals expected dot product. Oh, how exciting. All right, let's do this. Oh, sorry, expected dot product. Ooh, this should be plus equals. My bad. Dot product. Ooh, stack smashing. This is interesting. Why is this the case? Stack smashing is quite interesting. It's like overwriting things. Not exactly sure what that is, but hold on. Um, yeah, okay. Fixed length buffer, blah blah blah. Yeah. Cursor adjacent data on the stack or overflows triggered. Yes. Okay, perfect. So yeah, I think that yeah, that makes sense. Okay. I believe what's the issue here? Hmm. It's successful, but there's stack smashing. Let me actually just make this I. Let's not cast these to floats. We shouldn't get, we should still, it's probably the same issue, but okay. Ah, yes, the dimensions. This should just be size of floats. Yeah, okay, because C is one element. Well, why is there an issue here? CUDA mem copy C. Ah, yeah, because this should also be, we're only allocating size of float here. That should work. There should be no stack smashing here. Why is the assertion failed? Okay, we want to make sure C0, yeah, C1, it's going to be size of float. This should also be size of float when copying back. What's the issue here? This is quite interesting. CUDA malloc, that should be fine. DAA BBB size times size of float. mem copy host to device, device to host. Yeah, that's not an issue. That's not an issue. DC size of flow cadet device to host. That's not an issue. Let's look at the stern shared flow integer I equals block them x times. Ooh, that should have been a plus. There should be no issues here. Huh. Okay. Block them x times block id x dot x. It was a good catch anyways. Local I. If I equals size shared mom local I equals ai times bi. Yeah. Sync threads. If local I is equal 0, yep, integer sum equals 0, yeah, we're going to initialize the sum, k equals size, sum equals sum plus shared mem k. After the loop, we're going to see c0 equals sum, and we're going to close it out. There should be no issue here. Plus thread idx.x. Constant inch size equals 8, float a size, b size, c1. Huh. Why is there stack smashing? Dot product, yeah. CUDA free. That should be at times. Now that should work. Great. Sorry about that. Gotta be careful. All right. Convolution is a bit hard. Writing the executor is not that hard, but writing the kernel is quite difficult. We established threads per block is 8. The max convolution, which is the size of your conv, is going to be TPP is going to be max conv is going to equal 4. TPP max conv is going to be the addition of both. So we're going to create shared memory for both. We're going to create 2 shared memories. We're going to create we're going to do shared. We're going to make this. One is going to be size 12 and the other is going to be the rest. Yeah? We'll talk about this later. Again, if you want the intuition behind this, please do Sasha's notebook. It gives you a much better visualization of why we want the shared mem to be this size. And also watch his walkthrough, which is very well done. This is purely just from an engineering standpoint, with some with some logic of the puzzles thrown in there, but mostly just engineering. All right, this is just, sorry for boring you with all the initialization stuff. By the way, when you do my notebook that's on my GitHub, you don't need to implement these executors. You can just implement the kernels and then run the executors, and it'll run some of these test cases for you, so you don't have to deal with any of this initialization. So we want to check if local I is less than, we're going to work only with the locals for now. If local I is less than B size, shared B local I is going to be less than B local I. However, in which case is it not? That's when you have your convolution extending over the edges of what's actually written. So we're going to say int local I2 equals local I minus B size. Int I2 equals I minus B size. And then we're going to do if I2 plus TPB is going to be less than A size and a local I2 is less than B. This is going to be shared A local I plus TPB. Let's make this I2, my bad. Equals A I2 plus TPB. Now what's going on here, right? And we're going to do essentially, if your local I2 is over the edge of the convolution, we are going to initialize another set of index, and we're going to write that to shared memory at the specific location and then access that later. So essentially, if you have something in shared memory and you're doing a convolution over that shared memory, there's still memory positions that it needs to read that haven't been loaded into shared memory, especially for the end of the things that have been loaded into that shared memory. So for example, if you have 8 elements and it's trying to convolve the last 3 with the ninth position, then you don't have that. So you need to load that into shared memory as well in order to do the convolution. Right? Into sum equals 0. We're going to do the convolution now for integer j equals 0. So if I plus j less than a size, why do we do this? We want to make sure that the indices are, this is just a standard convolution formula, by the way. A local I plus j times shared b j. That's a convolutional operation. It's like going through the indices at specific places, adding them up, multiplying it, and presenting your sum. So if I that's quite a simple. That's the kernel for you. It's quite a long one. Now we're gonna do the main. The main is going to be very similar to 2D. I would say it's quite similar to this. Yeah, we're just gonna say b is size minus 2 for example's sake. In reality, it can be whatever size it wants because that's your convolution operator or your convolution or what that's what you're convolving your original array with. So AI equals that and bj equals that. Blah blah. We're gonna CUDA malloc that. We're gonna do be size minus 2. Dim block 3 dim. We're not gonna need that because we already have blocks per grid. So we already have TPB. So we're gonna say int blocks per grid equals size plus over, right? And then we're going to say int shared size A equals size of float times TPB max conv, and int shared size B equals size of float times max conv. So your shared memory size is 16. Does this make sense? Like how your operators are moving? You really have to dig deep down and understand what the convolution operator is doing and how the memories are being accessed. Again, Sasha Rush's notebook is very good for that. So integer divides b, yes. So now this is going to be blocks per grid. TPB shared size A, shared size B. Yes. Add side minus 2 to that. Size times size of floats. CUDA device to host. CUDA free DA, DBDC, and then for I, assert. So just for example, we're going to say this is 5, and we're going to have a hard-coded value in here to make sure that this works. Yeah. So this is going to be equal to 5, 8, 11, 4, 0. We're going to make sure the convolution operator is correct. If so, 1D conv is success. We have an issue. 14. What is the issue here? Where are we at? Uh, hmm. It sucks I can't get a line number in here. This should be like this. That's unfortunate. The ADBDC, yeah, that's right. Ah, it should be. Become 1D. It should be X. This should work. So from an engineering standpoint, do you see how, why is this? Huh. Let's print these out and see what's going on. So the first thing is 8. The first value is 8 for some reason. Let's examine why. Okay, so shared mem. Shared memory is plus TPV max com, block IDX X, block dim X plus thread IDX X. Shared local I equals AI, shared A. Shared B local I equals B local I. correct, less than b size. Else int local I2, local I minus b size, I2 equals I minus b size, I2 plus TBB is less than a size, and local I2 is less than b size. Shared local I2 plus TBB equals a I2 plus TBB. And we're going to sync the threads. Okay, perfect. That makes sense. Okay, I'm not sure why the indent is not working, but okay, anyways. Okay, for integer sum equals 0, is j equals 0, j is less than b size, j plus. Yes, that is the correct logic. I plus j is less than a size. Sum plus equals shared a local I plus j times shared b j. And then if I is less than a size, ci equals your sum. Now integer main, we have constant integer size a, we have size minus 2, c1. For integer I equals 0, I is less than size, I plus plus, a I equals, let's just, you know what? Let's just do I here. Doesn't matter if it's floats. dA to B to C, that's an issue if that's size. That should be chromatic. Size minus 2, size of floats. Let's just call this C1. See what happens. Okay. Blocks per grid. Shared size A, shared size B. That shouldn't make a difference, but it's okay. Conv1D. Hmm. Looks correct. Quite interested to know why it wouldn't be. Size 5, size minus 2, AI equals I, BJ equals J. Let me just do, that's an issue. There we go. Okay, sorry. J went way too far. It started probably overriding memory locations. Okay, cool. We're going to implement the prefix sum. Implement a kernel. Thanks for sticking with me there, by the way, guys. Appreciate you. Prefix sum, we're going to implement a kernel that computes the sum over A and stores it in C. If the size of A is greater than the block size, only store the sum of each block. Do this using the parallel prefix sum algorithm in shared memory. That is, each step of the algorithm should sum together half the remaining numbers. So you're going to sum half, sum half, sum half, sum half. This can be done quite easily with exponents. Again, refer to Sasha's notebook if you want a more detailed explanation, but here we're just going to implement the kernel. Extern shared. We're going to call this cache. Integer I equals block ID x dot x times block dim dot x plus thread ID x dot x, and oops, we're going to do int local I equals thread ID x dot x. If I is less than size, we're going to do cache local I. Make sense? We're going to sync threads after this. Now we're going to implement this logic. For integer p equals 0, p is less than 3, p plus plus. Why does this matter? Why are we doing it less than 3? Remember, for an array size, usually you'd be able to sum it with 8 moves. 2 to the power of 3, half the remaining, half the remaining, half the remaining. So we're going to do it like that. We're going to, so we see we include math at the top. This is going to be important. So we're going to do 2 power of p. That means if local modulo k, modulo k times 2. That means if the index is more than 2 times, right? So for example, local I is 5, k is 2. It's going to be k 5 modulo 4, which is 1. That's not equal to 0. However, if it's at the point in which you are summing, and local I plus k, if it's within the bounds, we're gonna do if we're within the bounds of the block, then we are going to cache local I plus equals cache local I plus k. Make sense? That should be equal. And then from here, we're going to sync threads. And we're going to do if I is, because we're setting cache to something, right? So C equal cache local I. Cool. This code will make sense. Now, this prefix sum should be the same as another one. So I think it's close to this one actually. Right? N equals 4, and Cn, static cast, we're going to float it to that. CUDA malloc, CUDA memcopy, n times size of float, correct. Test for block equals n, and blah, 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 blah. dA, dc size, we're going to call this prefix sum, right? CUDA memcopy, CUDA free, and this one. We're going to just, for simplicity's sake, based on the array that we've created, which is 0, 1, 2, 3, 4, 5, or 0, 1, 2, 3, 4, I believe, your sum should be 10. And you're going to say, in this case, my sum is successful. Yeah? Oh. What is the issue here? Integer p equals 0, p plus plus, integer k equals pow 2 comma p, if local I modulo k times 2 equals 0. Let's print. Oh, this should just be mem copies as a float. No. Print it out, see what happens. With 0, that's gonna be tough. Oh, it's 6. Huh. Oh yeah. That should be 10. Yeah, there we go. Okay, bet. That is correct. Okay, so does this make sense why we're doing this? So, for example, for an array that has 10 elements, right? K is going to cycle between 2, 4, and 8. Sorry, it's going to cycle between 0, 2, 4, and 8. We're looking for positions. So if local I equals like 7 and K equals 2, sorry, odd positions are left out, by the way, because local I, if it's 7 or 5 modulo anything, is not going to be equal to 0. So when it's the odd positions, let's say like 0, 2, 4, 6, 8. If it's 6 and K equals 3, but K will never equal 3, right? If it's 4 and K equals 4, and it's less than that, we're going to add the sum of local I, in this case is 4, plus K, which is going to be 2. So cache 6. So it's essentially like you're you're only going to get select positions, but then by using the index K, you're going to add positions that you would never get with your modulo in the beginning. Um, but yeah, go ahead and play around with it in Sasha's notebook. The visualizer in there is really good. All right, cool. We're gonna do the access sum. Access sum is pretty much the same thing as we had done earlier. However, since it's an access, we're gonna do it over the sum. We're going to add a batch variable. So we're gonna take this as our kernel, right? We're gonna add integer batch equals block ID x dot y. We're going to calculate a flat index. Integer flat index equals batch times size plus I, according to our same algebra that we did before, right? And we're going to, since it is a matrix, we're only going to use the flat index that we want, right? And we're going to do, we're actually going to put this all inside the loop. So yeah, we're going to sync threads, and then we're going to stick all of this inside. The reason why is we really want to make sure it's within the size of the matrix. That's super important. Okay. Yeah. This should be a good kernel. Why does it? We're essentially doing the prefix sum over the axis. There's nothing new here. We're taking what we did before and we are applying it to the new matrix. Um, this one we're going to write from scratch just to give you guys some practice again. I think it's important. So we're going to do constant int size equals 5, and then float or constant int num batches. We're only going to do this in one batch. Float a size times num batches. If we're doing a sum across two axes, then we'll do 2 for integer j equals 0. J is the sum num batches. J plus plus. For integer I equals 0. I is a then size I plus plus. A j times size plus I equals I. What is that doing? That is initializing A as your matrix with that size. Technically, you do A I J equals I, but you can do flat indexing in normal C++ too. Okay, let's do that. CUDA malloc size times num batches times size. Well, this should just be num batches times size of foot. All right, cool. Now we've malloc that. We're gonna do CUDA mem copy d a size times. That's all we want. We're gonna do host to device. Then 3 threads per block again should be should be size 1. Remember, we're only doing it across one axis, so we only need the threads across that one axis. However, we need to do it as a 2D thing because we're accessing a row or a column in a matrix. Right? And then we're going to do int shared size equals batches. Oh, sorry. Threads per block x times size. Or it could just be times size of flow. Yep. Now we're going to do the same thing. Axis sum blocks per blocks per grid, threads per block, and shared size DADC size. Boom. Okay, now we're going to do CUDA mem copy CDC. I forget what is C size again. Num batches. Device to host. And then we're going to do CUDA free DA, CUDA free DC, because that's all we need. Then we're going to do assert C0 equals 10, because that's how we initialize our array. Axis sum is successful. That makes sense. Yep. There should be no errors here. Where am I initializing DB? 48 DB. I don't have a DB anywhere. Could have. Oh, we don't need to. It should be C. Ah, we have a memory issue. What is a memory issue? Invalid at the thread 1. Ooh, that's an issue. Okay. Batch equals block IDXY, local I equals thread IDXX. This is correct. Class system size cache local I equals a flat index, sync threads. 4p integer k equals pow 2p. Ah, this should not be blocked mx, this should be size. There we go. That should work. No, another memory issue. Okay. Cache local I, we're going to sync threads after we do this. And then if I is the size c batch equals cache. The logic makes sense here. Let's try constant int size 5. J times size plus I equals I. Yeah. Float the ADC. CUDA malloc. Size times num batches size of. DA, A, size times num batches. Then 3, size 1, num batches. It should be fine. Not sure what the issue is here. Where's the memory issue? Cache, we set integer I equals block, integer I local batch equals block ID x.y, flat index, batch times size plus I is less than size, cache local I, a flat index. name. What's the issue here? This is quite interesting. Chromatic at DA size times non-batches as a float, DC non-batches times a float, a whole sheet of 5 size of floats, non-batches. Ten 3 threads per block, blocks per grid. Sum is successful, but we get this strange memory error. It's a very interesting issue. I'm not sure what this is. Integer flat index, batch times size plus I. I is the size, cache local I equals a flat index. Sync threads, yes. IUP was 0. That whole loop is fine. Let me just make sure that that whole loop is fine. I don't think there's any difference. Good question. Where is this? I don't know. Yeah. Someone say in the comments what you think the memory issue is. That'd be awesome. Can't seem to find it right now. Might have to move on. Let me look it up one more time. You know what? Let's. I don't think it's an issue with the kernel. I think it's an issue here. Floats A times num-batches. C num-batches. Num-batches equals 1. J equals 0. J is less than num-batches. J plus plus. For I equals 0, I is less than size, I plus plus. A, J times size plus I equals I. We're going to malloc that size. We're going to mem copy that size. We're going to write it back. I'm not sure the issue is. Someone can help me out in the comments. I appreciate it because I can't see exactly where the issue is. I think it has to do with an issue of writing to C. C is initializes having one thing. So let's do this. Let's actually do this. Let's say okay, cool. I think it was just an issue with writing to C. Um, it in the main, or sorry, in the kernel here, we were doing too much writing. C that only had one memory location, and we were trying to write to a bunch of it. Okay, cool. Matrix multiplication. This is probably again one of my favorite ones. We're gonna assume the threads per block is gonna be three. We're gonna have two shared memories, one for A and one for B. So why are we doing this? Because I'm gonna say A is threads per byte times or threads per block times threads per block. Okay, now we're gonna go through. So for integer k equals 0, k. Why are we doing this? We're jumping every three. Because you know matrix multiplication, you have to jump. If I is less than size and I, k plus, right? A shared local I times TPB plus, we're gonna index. This is just for like what we actually load into share memory. Why are we doing it like this? Do you see this? Because remember, rows, columns, rows, columns, rows, columns. That's how it works for matrix multiplication. So, right, B shared local I times TPB plus local J equals B local I plus K times size plus J. What is this exactly doing? We are copying to shared memory. We need to be strategic about the indices that we're copying to shared memory. So for example, right, K is less than size. So like, let's say K is 0 now, right? Local I is 0, local J is 0, right? A 0 is going to be equal to A 0 in this case. Same with B. B 0 is going to be equal to B 0, right? Which reminds me. So now what does that mean, right? Since A 0 is equal to, but then what happens, right? Every location, so A local J equals A local J. B local I, no, B local J equals BJ. Now, when K equals TPB, what happens? Now, local I equals like 0, 1, 2, 3, 4, 5, 6, right? K is going to be that adding factor for A. So it's going to move on to the TPB. So for example, local I is 1, TPB is 3, and local J is 1. You're going to get A shared 4 equals A of 1 times the size, which is like, let's say 5, right? Plus K, right? Which is your TPB, which is 3, plus local J, which is 1. So you're going to get A, which is the index. But we know that K plus local J is going to be less than size here. We have to make sure that because I times size is going to be pretty big. Does that make sense? Again, reference the walkthrough made by Sasha Rush for a more detailed explanation about why this works. I wish I had a visualization to show you, but I don't at the moment. So we're going to say integer local k equals 0, k local k is less than tpb, k plus plus. Remember, our shared memory is only tpb times tpb, right? So we only want to load into shared memory what we care about locally in terms of these matrix multiplications, right? Only the certain rows and columns that we need in order to make it work, correct? So if k plus local k is less than size, this is where we do the actual multiplication. Sum plus equals a, a shared local I times tpb plus local k, right? Plus b shared local k times tpb plus local j. This is indexing again, simple indexing. All right. Oops. Now we're gonna get out of this for loop. So if I is less than size and j is less than size, we're gonna then say c I times size plus j equals sum. Does that make sense? So again, looking at Dr. Rush's visualization, we see that um, there is, since you have a certain amount of threads per block, you can only do certain parts of the matrix multiplication at a time. So you need to access a certain row and a certain column in order to get a certain value in the resultant matrix. And so you need to load those into shared memory so that you can end up doing those computations with the threads that you have in that block. Um, so now, sorry, we're going to write the main thread or the main. So we're gonna keep this simple. We're gonna do 2 by 2 matrix multiplication. Yeah. This is just initialization. Don't worry about this. So I'm going to say A, I, J equals I times J, and B, I. This is totally random, I plus J. Cool. Now we're going to say float D, A, D, B, D, C, CUDA Malik. So we're just going to say integer double size equals size times size. So we're going to say by the way, size of float, if I didn't mention this earlier, is important as well because that's the amount of bytes a float takes. And that's how much memory you are allocating. Okay, so CUDA mem copy D double size host device CUDA. Yeah? Cool. We're going to do integer blocks per grid equals size minus TPP plus 1 over TPP like we did before. dim3 blocks per grid equals blocks per grid, blocks per grid. dim3 threads per block, TPP, TPP, and then dim int shared mem size equals 2 times TPP, right? Times size of float. Does that make sense? So like we want the shared memory to be TPP times TPP. We're going to allocate 2 of that in here. Yeah? We're going to do map mul, blocks per grid, threads per block, and shared mem size. Right? Boom. And then DA, DB, DBC size, CUDA mem copy DC. We're going to do device to host. And then CUDA free D. And then assert. We're going to just hard code this just for demonstration's sake. Okay. Oh, um, um, blocks per grid has already been declared. Let's just do PPG. Yeah? Call it PPG. CUDA mem copy. Oh, the assertion failed. Again, we're gonna get hit with a memory error. Okay, so let's take a look at this. So we have our extern shared mem plus TPP test TPP, block ID XY, block dim XY, thread ID XXY, local I, thread ID XX, thread ID XY, float sum equals 0. 4, integer I equals K, or K equals 0, K is less than size, K plus equals TPP, 5 is less than size, and K plus local J is less than size. A shared local I times TPP plus local J equals A, I times size plus K plus local J. If J is less than size and K plus local I is less than size, correct? B shared local I times TPP plus local J equals B local I plus K times size plus J. Sync threads after that. For integer local K equals 0, local K is less than TPP, K plus plus. If K plus local K equals size, oh, local K plus plus. Good catch. Oh, okay. That still failed. Anyways. Local K plus local K is the size sum plus equals A shared local I times TPP plus local J times TPP It should be local K. Again, same thing failed. Okay. Now, after that, after the for loop, if I is less than size and j is equal to size, I times size plus j equals sum. Constant is a for float malloc size times size of float, size times size double size of float. PPG size minus TPB plus, oh yes, it should be size plus TPB minus 1. I don't know why I did that. That's the wrong. Ooh. There's no compute sanitizer issues, but the initial thing failed, so let's do. Let's look at that. What's the issue here? What is that? It's 1. Okay. It shouldn't be 1. 0, 1, 2. 2 times TPB times TPB, BBG, BBG. Yeah. There's an issue with the kernel itself. So let's look back at the kernel. Shared mem, TPB, float sum. I is less than size. Yeah, that logic makes sense. Local I times TPB plus local J was A times I times size plus K plus local J. If J is less than size and local I plus K is less than size, local I times TPB plus local J. B equals local I. Huh. Good, good, good. Local I times TPB was local K times TPB plus local J. Yeah. Mm. It's not plus, it is times because we are doing the matrix multiplication. Sorry about that. Okay, does this make sense? So it really helps look at the visualization, but we are loading these matrix multiplications into shared memory so that we are doing the multiplication for the rows that matter and for the columns that matter, and then storing it in the output within the threads per block. We initialize it here, mem copy it, shared mem size, and then assert these are true. And over here, we're making sure the indices are correct. Indices are probably the most important thing in GPU programming. And we add them in here and make sure our indices reference the correct place and are good to go when it comes to the columns and the rows of the shared matrices.
All right, thanks everybody for watching. I know that was long-winded and there's a lot of stuff to cover, but I'm hoping that you enjoyed working with GPUs at a low level. Check out NVIDIA's documentation for C++ bindings for more information. Um, by the way, in the middle of the video, I used a search engine to look what a stack, um, or what the stack issue was. That's Perplexity. Go check out Perplexity. Huge fan. Um, and also, please, before you do this notebook and before you watch this video, go, and I'm probably saying this too late, but go watch Sasha Rush's or Dr. Rush's video and do his notebook on the GPU puzzles. It'll give you a really, really good intuition for some of the kernels that I implemented really quickly here. I did that notebook first and then translated that into C++, and learned all of the other necessary things in order to make it run, or in order to make the CUDA run on the with the NVCC and then also on the GPU and then within Colab as well. So go ahead and check out that video and yeah, enjoy coding on the notebook. I hope you enjoyed the video and keep and continue to build on your skills on coding on GPUs. I think it's a really important skill to have as a machine learning engineer, and it really gives you an intuition on how these things are built. Um, and yeah, appreciate everyone watching, and have fun the rest of your day. Take care.